Hey everybody, my name is Zach Byerly. I am a postdoc at LSU Center for Computation and Technology, and my boss is Dr. Hartmut Kaiser, who's a computer scientist. And I'm here to tell you guys today about a project that we are working on, and we're very, very excited about it. The project is called STORM. STORM is an acronym, sort of, but it's one of those acronyms that's a real stretch. A scalable toolkit for an open community supporting near real-time, high-resolution coastal modeling. So, usually the second slide in this talk is a slide that describes what ADCIRC is. I took that slide out of this talk. I replaced it with this figure that we made for a poster recently, and I thought it would be a good way to sort of outline the scope, the broad scope of this project. So the STORM project is, one part of it is to combine ADCIRC with two modern C++ parallel computing libraries, one of them called HPX, the other one LGD or libgeodecomp. But the STORM project is broader than that. We also are going to do research into what I have perhaps unfairly lumped together and just called DG methods. Essentially, a lot of research into advanced solvers that I know nothing about. And then the other component of the STORM project is going to be to continue this tightly coupled integration of two other different software products, ASGS, which of course Jason develops, and then CIRA, which is the Coastal Emergency Risks Assessment website, which is for delivering ADCIRC results into the hands of decision makers and emergency managers. I'm almost exclusively going to be talking about the development of the ADCIRC HPX LGD hybrid code. So our goal is to build sort of a next generation ADCIRC code. And I put several buzzwords up here on the slide: sustainable, extensible, scalable, and flexible. We want something that we can use as a basis for our code that will evolve over the next 5, 10, 20 years. We want something that's extensible so that we can add new features to it, new solvers. We want something that's going to be scalable. Computers are getting bigger and bigger and bigger. Not only are they getting bigger, but they're also getting more heterogeneous. GPU accelerators, Intel Xeon Phis, and of course we want something flexible. We also want something faster. That's kind of in with the scalable thing. So before I talk about how we can make it faster, I need to talk about why codes are slow. This is a slide I stole from my boss. I'd like to introduce you guys to the 4 horsemen of the apocalypse. Starvation, latencies, overhead, and waiting for contention resolution. This is another really cute acronym because you put all those together and it spells slow. Starvation is insufficient concurrent work to maintain high utilization of resources. So in other words, you don't have enough parallelism to keep all of your computing resources busy all the time, and that's inefficient. Latencies are just the latencies that you get from the time it takes to move data from one part of a cluster to another part of a cluster. Overheads are the extra work that you add to a serial program in order to make it parallel. And waiting for contention resolution is kind of sort of like starvation, except for you have a bunch of tasks that are relying on a single computing resource, and they get sort of backed up like a traffic jam. So what we want to do is we want to use HPX to overcome some of these problems. So some of the things we can do are we can use fine-grained parallelism. In other words, we take the work and we break it down into smaller and smaller bits. And if you imagine taking a big barrel and filling it up with tennis balls, the volume of the tennis balls is going to be far less than if you were to take that barrel and fill it up with sand. So you have smaller pieces of sand filling that barrel, so you're able to use more of those computing resources as a result. HPX allows us to focus on data dependencies. In other words, this one piece of work that needs to be done. For example, the update to one subdomain relies on having the results from the neighboring subdomain at the previous time step. And we focus on those types of data dependencies rather than the way that ADCIRC is written now with MPI, where we explicitly communicate boundary zones between neighboring subdomains. This allows us to effectively hide the latencies rather than try to minimize or try to avoid them. So this approach allows communication and computation to be happening simultaneously, instead of the way that it happens now, where we start one time step, we do a spatial loop, all of the new values are computed across all of the different subdomains, and then everybody finishes their computation, they all stop, they all send each other boundary values, and then it's time for the next time step and they all start computing again. So you have computing happening, computing stops, communication starts, and then communication ends and computing starts again. There's no overlap. With this approach, we're fluidly overlapping communication and computation, so latencies, large latencies don't matter nearly as much. HPX also allows us to do adaptive locality control versus static data distribution. In other words, dynamic load balancing. So let me tell you just a little bit more about HPX. So HPX is a general purpose runtime system. So it allows you to take a program and run it in a parallel environment, whether that parallel environment is a shared memory system, a laptop with multiple cores, a distributed memory huge cluster, or even a heterogeneous environment, a cluster that has GPUs attached to it, Intel Xeon Phi attached to it. It's based on a theoretical foundation, a theoretical model called Parallax. It's a standard-oriented API. We've already written applications and demonstrated that with some classes of applications, we're able to outscale and outperform existing codes based on other parallel programming paradigms. It's published under a relatively liberal Boost license, and it's got a really open, active developer community. So this is what a proposed software stack for this next generation of ADCIRC would look like. So we would retain these. Does this thing have a laser pointer? So we would retain these ADCIRC physics modules up here. So all of the important Fortran subroutines that update values on an individual subdomain would remain intact. And we would then use a sort of layer of glue here, an application code that would manage the interface between the Fortran subroutines and C++ code. That application code would then run on top of another library called libgeodecomp, which which I'll tell you about it in a minute. And then libgeodecomp would then use HPX to do the actual parallelization, the communication between all these different communicating computational resources. So what is libgeodecomp? libgeodecomp stands for Library for Geometric Decomposition Codes. But essentially what it is it's an auto-parallelization library for computer simulations. It's developed by our colleague Andreas Schaefer, who is at Friedrich Alexander University in Erlangen, Germany. He's actually in Baton Rouge right now. It's also open source, both HPX and libgeodecomp. You can go on GitHub and Bitbucket respectively. You can see the code, you can download it, you can play with it. It's also libgeodecomp is written in C++, as is HPX. Libgeodecomp though supports custom kernels that are written in C, C++, or and this is important for us, Fortran. And the real goal of the libgeodecomp library, and the reason why we're incorporating it into our project, is that it's really designed to separate the domain science, in this case coastal modeling, coastal engineering, from performance engineering, load balancing, parallel computing algorithms. We essentially want to take the domain science and the computer science and separate them in the code so that we can have computer scientists building the best computer science parts of the code, and we leave you guys to focus on doing the best coastal engineering that you guys can do. So libgeodecomp already has some history with legacy code and even with Fortran legacy codes, and it's already been demonstrated to be scalable, portable, efficient. So the way LGD works is you have a couple of different things that are provided by the end user, the application developer. You have an initializer routine here, which basically takes care of everything that you need to do to set up the problem. So in the case of ADCIRC, that would be things like reading in all the mesh files, building the ADCIRC mesh, reading in initial configuration files, initial conditions. And then the second thing that the user provides is essentially an update function. So for every unit of work, you provide all the instructions that you would do to update that unit for one time step. And then the libgeodecomp library supplies then the simulator, which is really the heart of libgeodecomp. The simulator takes care of all the data dependencies between your individual cells. It takes care of the temporal and the spatial loops. And we have the option of either using built-in, already developed writers and steerers, or we can customize those and add those in as we need to later. So that brings us to some of the work that we've already started doing on this project. We've been developing a proxy application, something that will simulate the workload and much more importantly, the communications patterns that happen inside of an ADCIRC simulation. So it's called Game of Life ADCIRC. It runs on a decomposed ADCIRC computational mesh. So we take, in this case, the Shinnecock Inlet mesh. We break it down using ADC prep, just like you would do for a normal ADCIRC run. We then read in all of that computational information into this application, and instead of doing all of these complicated physics, we just do a very, very simple cellular automata game of life kernel. I don't know how many of you guys have heard of Conway's game of life. It's essentially a code that the behavior of each point on the grid is dependent on the state of its neighbors at the previous time step. And so we've developed this application code, this proxy code. So this is running on top of libgeodecomp, which is running on top of HPX. And this simple game of life kernel is actually written in Fortran, and then the Fortran subroutine is compiled and then linked and called from the C++ application code. So this is a little bit sort of what that looks like. This is real code, but it's not complete code. So you can see here, this might be a little bit easier to look at. This is just the essentially the update piece. So you have an array of the current state of the mesh, and then you go through and you loop over all the nodes. You loop over all the neighboring nodes, and you then apply some rules to determine what the next state of that node is going to be. So for this set of rules, all it's doing is saying if any of your neighboring nodes are alive, then at the next time step you become alive. And if you're alive at one time step, then the next time step you become dead again. So it's really just a very simple thing to demonstrate that we have sort of the boundary value exchange and everything working properly. So this is in a kernel.f file that's compiled with gfortran, and then over here you have the C++ side of the code. This is in that application code part of the software stack. So this is written on top of libgeodecomp, and that code is actually much longer than this, and even these two functions are much longer than this. But you have this ADCIRC initializer routine here that I actually took out all of the actual code. But the ADCIRC initializer reads in all of the Fort 18, Fort 80, Fort 14, all of the files that come out of ADC prep when you take an ADCIRC mesh and break it down. And then this is the other important piece, this domain cell update. This is what actually gets called once for every subdomain for every time step, and it actually does a lot of other things, but the important thing it does is it calls that Fortran kernel from the C++ code. So this is a movie. This is created using the Sierra Viewer application, and I have no idea if I'm going to be able to actually get this to play or not. It would be really great if I could. So you can see this is the Shinnecock Inlet ADCIRC mesh here. So this is running. This has been decomposed into 32 or 64 different subdomains, and it's running on multiple threads and on multiple nodes. So in sort of a fully parallel distributed memory environment. And so what I've done is I've started out with all of these different nodes are, it does take a minute before you can tell that it's playing. So it may have been playing the last time you clicked it. So what I've done here, this is obviously not the whole mesh. It's playing, I think. No, not anymore. So what I've done here is I've taken this entire mesh and I've initialized the entire mesh to dead, which is red. Well, That's too bad because this is a really cool movie. Basically, what I've done here is I've seeded a single one of these nodes that's off the screen here as being alive, and then when all of its neighbors see that they have a neighbor that's alive, they all become alive, and then essentially this sort of shockwave moves through the grid. You can see it sort of spreads out like this. It hits here, this bottleneck, and then it spreads out into this inlet. So it was a really cool movie, but I'll have to take my word for it. You can also go on our website and watch it. So, so now that I've tried to show you that, this is the obligatory CIRA slide. I think most of you guys already know what CIRA is. CIRA is the sort of the very end stage of this whole end-to-end project, I guess. CIRA is a very intuitive, very easy to use tool that is really designed to get the most important information from these ADCIRC results into the hands of emergency managers, decision makers. So you can obviously display the ADCIRC results from a particular run, inundation, but then you can also overlay things like the NHC consensus track. You can look at gauge stations and compare predicted gauge, historical data from the gauge, and then predicted ADCIRC water levels for that gauge. So it's a very cool, very useful tool. So now that I've told you guys all about what we plan to do for creating this next generation code, I sort of wanted to outline what we consider are our ground rules as we approach this problem. Making ADCIRC faster and making it scale better is not going to be worth anything unless we can get the results from this new next generation ADCIRC to exactly match the results from the MPI-based ADCIRC. So we consider that a requirement. We also want the current ADCIRC MPI source code to essentially remain intact. There may be some refactoring of the code that needs to happen in order to facilitate the use of these Fortran subroutines with the C++ code. But the idea is that the ADCIRC MPI source tree would remain intact, would be continued to be developed. Physics algorithm developments would continue to take place inside this ADCIRC MPI source code. And the way that we plan on keeping these two projects in sync is that we would actually, in the build system of the next generation ADCIRC, we would point to the source code for ADCIRC MPI and in some sort of automatic or semi-automatic fashion pull all of the important physics subroutines from the MPI-based version of the code, incorporate them into the next generation code, And so that way we don't have to leave anybody behind. Everybody can keep running ADCIRC MPI that wants to. Anybody that wants to use the next generation HPX version of the code will be able to take advantage of any updates, any improvements that are done to the MPI-based version of the code. And of course, in order to help enforce the very first one of these things, we will develop a automated testing suite. So we would take a whole bunch of different example problems, and we would use some sort of framework, maybe ASGS or something similar, to run these test problems on a nightly, weekly basis to continue to ensure that no matter what changes are made, either in the MPI version of the code or in the sort of computer science half of the next generation code, that we can continually ensure that the results that we get from both codes are matching up exactly. So, with that, I want to thank all of our collaborators, Johannes, Rick, Clint, who everybody here knows, I'm sure. Robert Twilley is the director of Louisiana Sea Grant, and is that what at LSU? Jason. My boss is Hartmut Kaiser. He is the leader of the Stella Group. The Stella Group is the group that, among other things, is developing HPX. And of course, we have to thank the NSF. And last but not least, we've got what we think is a pretty cool looking website. It's got a lot of information about a lot of the different pieces of this project, including the pieces of the project that I didn't tell you about today. So I would encourage you guys to go check out our website.